Probably you think of digestion and so on, breaking down food and all the rest of it. And that part of it, but it's only one part. In fact, breaking down food, digesting food, is catabolism. It's breaking down materials. But then we take those materials and rebuild them into new materials. So catabolism is breaking down materials. For example, eating a hamburger. Hamburger is meat. Meat is protein. So breaking down the protein, getting amino acids, that's your catabolism. And then taking the amino acids and rebuilding them into some new protein. That would be anabolism. So actually, metabolism is both breaking down food into its raw materials, and then using those raw materials, fatty acids, amino acids, and so on, using them to rebuild new stuff. We do it all the time. But there's actually a third part of this that nobody ever thinks of, and that is catabolism provides energy. We get energy from our food. We don't just get the amino acids and so on, we get energy as well. So it turns out we're getting that energy, before I forget, so again, if some of you want to come back and get your gram staining labs later and kind of rework them, that's okay with me. Or you can just leave them here as you wish. So, because there's obviously quite a bit of information tonight that you hadn't had before. So up to you if you want to come get it or not. At any rate, it turns out energy is stored in chemical bonds. So if you break a chemical bond, you release energy. Now that's the idea behind ATP. You're all familiar with ATP from other classes. ATP has lots of energy in the bonds. Once we break the bond of ATP, the energy is released, and we use it. But all chemical bonds have energy. Not as much as ATP, but they still have energy. But that raises an issue, or raises a question. What exactly is energy? We all use the term. We all say energy all the time. High energy, low energy, and so on. What is energy? It's electrons. Energy is electrons. We work by electrons. Another way of saying we work by electricity. The movement of electrons, the movement of ions. So we actually function by electricity. And my next comment here, metabolic reactions require electron transfer. So breaking down of chemical bonds releases electrons. And we use those electrons for energy. What we're going to be talking about for this whole chapter. Again, it's going to get tough, so if something's not clear, please do speak up. It's why we're here. And I know you're not going to study it until after the midterm. I understand that, but at least if there's something that doesn't make sense, let me know. Okay, so this now is a bunch of definitions. Oxidation and reduction. Oxidation and reduction. You're not going to need them just yet, but you will need them. Oxidation is defined as loss of electrons, loss of hydrogen, or the addition of oxygen. Any one of those qualifies as oxidation. So you don't need all three, you just need one. But it could be any one. Reduction is simply the opposite. Gaining electrons, gaining hydrogen, or losing oxygen. And once again, any one of those is okay for reduction. Now clearly that needs a little more commentary than that. So let's take a look at methane. CH4, that's methane, natural gas. Now, as you've all heard approximately 1 million times, carbon has 4 bonds. You may forget everything else when you leave, but you will never forget carbon has 4 bonds. Now, the thing is, all 4 bonds are to hydrogen. So you can't add any more hydrogen. Addition of hydrogen is reduction. Addition of hydrogen is reduction. But all 4 bonds are already to hydrogen. You cannot add any more. So therefore, methane is the fully reduced form of carbon. Methane is the fully reduced form of carbon. Got 4 bonds, 4 hydrogens, fully reduced.
So then the fat is saturated fat.
Think it through. Carbon has 4 bonds. Where are all 4 bonds going?
Oh, not all the way to hydrogen.
Going to carbon. Exactly. So, we can't add any more hydrogen. Again, it's full. That's why fully reduced. So if we can't do any more hydrogen, we cannot do any more reduction. Therefore, we have to do oxidation. That's all that's left. So oxidation, and we're going to ignore the electrons. For right now, ignore the electrons, both here and here. So either losing hydrogen or gaining oxygen. Losing hydrogen or gaining oxygen. So chemically, we cannot do that. We can't do it. Remember, hydrogen only makes 1 bond. So hydrogen can never be in the middle of anything. If it's in the middle, it's making 2 bonds. Hydrogen cannot do that. So if we're adding oxygen, it's got to be like that. Oxygen makes 2 bonds. Now that's oxidation. We added oxygen. We did not take away hydrogen, but that's okay. Remember, any one of these qualifies. We added oxygen, so it's oxidation. If we did it once, we can do it twice. And if we did it twice, we can do it 3 or 4 times. So each one of those is an oxidation. Well, we can still keep going. We can't add any more oxygen because, again, all 4 bonds are taken. So now we start taking away hydrogens. We can start doing that one. But we can't just take away 1 hydrogen. The bonding thing won't work. So actually, take out water. Take out water. Take out the OH, take out H. I won't bore you with the bonding deep. Yeah. Sorry, continuation of oxidation. But what we're doing now, we're taking away 1 oxygen, so that is reduction. Taking away 1 oxygen, 1 reduction, but taking away also 2 hydrogens. So 2 oxidations. So 2 oxidations, 1 reduction, total is oxidation, 2 to 1. And that gives us that. Gives a bond from here and spin down to here. And then I'll do it 1 more time. Take out the water again. Take out water again. So leaving the oxygen. Carbon dioxide. CO2. This is the fully oxidized form of carbon. So once again, 4 bonds, and all 4 bonds are to oxygen. So the fully reduced form, I'll come back to this in a second. The fully reduced form is methane, CH4, whoops, and the fully oxidized form is carbon dioxide. And everything else is in between, partly oxidized, partly reduced. So again, we're going to be using these definitions. The electron part, not so much for a while, but the others we'll be using as we go through the quarter. So, like you say, it's going to get kind of tricky. Again, I know you're not going to be studying this for right now, and I understand, but any questions on that? Is there anything there that you don't get?
But we have a quiz on this on Tuesday.
No, I don't think so.
Okay.
I don't think so. Your midterm is Thursday, and that's enough trauma for a while, so no quiz next week. Yeah. I'm sorry.
Would you mind
Could you,
or you can continue with your,
or just do it again?
Yeah.
Okay, I'll just do it again. So that brings us then to, yeah, just did that. So methane again, fully reduced CH4, and carbon dioxide, fully oxidized form of carbon. Now the other big topic here is this one. For all living things, where does the energy come from for life, and where does the carbon come from for life? So again, some definitions. Autotrophs, by definition, are getting carbon from CO2, from carbon dioxide, by definition. By definition, the heterotrophs are getting carbon from organic molecules. Remember from before sometime, carbon dioxide is just about the only carbon-containing molecule that is inorganic. Most molecules of carbon are organic, but not that one. So CO2 is inorganic. So carbon from CO2 makes the organism autotroph. The heterotrophs are getting carbon from anywhere else, from organic sources, which is all the other molecules. Energy. Phototrophs get energy from the sun. I know I only say light there, but from sunlight. And then the chemotrophs get, I say they're inorganic substances. In honesty, it's broader than that. It could be organic as well. So let's just say they get energy from chemicals, not from the sun. So the phototrophs get energy from the sun, the chemotrophs get energy from everywhere else, but mostly chemicals, like food. And what we call food is just chemicals, but we eat it. So let's put it all together. Photoautotrophs. So photoautotrophs are getting energy from the sun and carbon from CO2. What kind of organisms are those? You know what they are.
Plants,
Well, plants, but more broadly.
algae,
No, that's just more broadly. What do plants do? Photosynthesize. These guys are photosynthesizers. And I didn't want plants because it's more than just plants. Green and purple sulfur bacteria, I know you don't know what those are, but it's coming. Algae, although specifically green algae. Green algae. The green algae are the precursors of green plants. They have the same chlorophyll, they have the same various enzymes and molecules. The plants come from green algae. There are other algae. For example, brown algae. don't photosynthesize. Anybody know what brown algae is? And you do, actually. What?
Oh.
Seaweed. Brown seaweed is brown algae. And I mean, you weren't supposed to know that. I just figured something might. But at any rate, but they don't photosynthesize. So green algae does. Other algae don't. Green plants, of course, and also cyanobacteria, which used to be called blue-green algae. So the point of it is there's lots of photosynthesizers. And that's why I wanted a more general term. Yeah.
Are the green and purple sulfur in bacteria?
No. The green and purple sulfur bacteria. Because not all bacteria photosynthesize. Okay, so it turns out that the sulfur bacteria do not produce oxygen after photosynthesis. Let's take a look at photosynthesis. And of course, you know, we've all seen that since grade school. But here's the formula. Carbon dioxide plus water produces sugar plus oxygen. But if you just look at that formula, you cannot tell what the sugar is. We did 3 monosaccharides. We did glucose, we did galactose, we did fructose. All 3 of those have the same formula. So you can't tell by the formula. In fact, though, it's glucose.